Hi, my name is Manish Gupta, and in this video, I'm going to talk about personalization for query auto-completion systems. Let's start. What is personalization? To come up with more effective suggestions for query auto-completion systems, it might be better to come up with suggestions which are relevant to short-term session history of the user or to long-term user history across sessions, or it could be personalized with respect to the location of the user, or it could also leverage other kind of signals for personalization, like browsing history from the user. So what is personalization? Well, let's consider a user who typically has been searching for various kinds of books in this session. Right? So if the user typed in the prefix the great, then maybe we should show suggestions which relate to other books which start with the great. Similarly, consider another user who has been searching for a lot of movies in this session. Now, when she types in the great, possibly we should show movies which start with the great. Finally, let's consider a third kind of a user who has traditionally been a movies kind of a user, searching for a lot of movies, but recently she has been searching for a trip, for things related to a trip to China. In that case, when the user types in the great, we should show her the Great Wall of China right at the top. So that is what personalization can do for you in query auto-completion systems. In this video, we are going to talk about traditional machine learning methods that leverage personalization for query auto-completion. Then we will talk about the popular hierarchical RNN encoder-decoder model. We'll also talk about GRUs with user and time representations. And lastly, we will talk about transformer-based hierarchical encoder model for personalization. So let's get started. Let me talk about first about traditional machine learning methods for personalization. Now, personalization could mean several things. In the beginning, when people started doing personalization for query autosuggest systems, people started with simple things, with trying to do personalization based on demography attributes like gender or age group or location or short-term and long-term history, right? Those kinds of things. So prefix equal to I, if you look at that kind of that segment of queries which start with I, if the user is young and a female user, the most popular suggestion is Instagram. Versus if the user is a male user in that age group, the most popular suggestion is IMDb. In fact, here are some stats to show how the queries, the likelihood of the queries differs across age groups and across gender. So as you see, for IMDb, typically males in a particular age group essentially have a very high likelihood of putting up IMDb as the query, while if you consider the distribution for Instagram, you see that a lot of females below 24 age group, below 25, 24 age group sort of query for Instagram. This basically shows that using these demography attributes for personalization is meaningful and should lead to more effective suggestions. Right? So in this particular work, people focused on different kinds of demography attributes: age, gender, location, short-term, long-term history, engrams, and so on. So in fact, to be able to incorporate these as personalization signals in a machine learning framework, these guys essentially considered several features. Features related to previous query engram similarity. So this is short-term history, very short-term history, right? Average session engram similarity related to history for this session. Long history frequency, so number of times a candidate is issued as query by the user in the past. A long history similarity, so not the exact query, but hey, what is the average n-gram similarity with all previous queries by the user in the past? Yeah. Then there are demography based attributes which relate with candidate frequency over queries submitted by users in same age group, same gender group, same region group, and this has to do with candidate frequency and likelihood. So both normalized and non-normalized, unnormalized features. Lastly, of course, there are features related to the most popular completion method, um, which is basically the position of candidate in the MPC ranked list. So these two are more like non non-personalization based features, but the typical features which are used for ranking suggestions in an autocomplete system anyway. Yeah. So people use these kinds of features and worked with a supervised framework for training a model using labeled data from the past. So the query was which was eventually submitted, that is clicked in the autosuggest block, is considered positive, while the other candidates which were not clicked are called as negatives. Right. So learning to rank based methods were used, and people found that hey, these particular queries were the biggest movers, meaning these queries benefited the most thanks to the age group signal. So as you see, people below 20 are crazy about these kinds of things. However, people above 50 are more interested in queries of those kind. What was found among those features that we looked at, users' long-term search history and location are the most effective for personalizing auto-completion rankers. Also, people found that these supervised rankers, which used personalization features, significantly outperformed the existing methods, which just used the popularity-based two features, right, on the MRR metric by about 9%. These are the big movers or the queries which saw greatest movement in their accuracy based on location. So the locations, of course, is a hierarchical attribute, but you could group locations by zip codes. And what you see here is that certain kinds of things which are popular in certain parts of the US actually saw significant movement in terms of their accurate predictions. Okay, so that was traditional machine learning methods. Now let's talk about hierarchical RNN encoder-decoder model. So this kind of a hierarchical encoder-decoder model with a personalization in mind was proposed for map query suggestion. So suggesting queries on maps, right? Uh, the hierarchy comes into picture because you can think of a session as consisting of queries and queries as consisting of words. So these folks essentially built two-layered LSTMs, as you see here, for encoding the current user session. So the hierarchical contextual attention model, RN model, has been proposed specifically in this particular work for map query suggestion. So here are some input examples. There's the user who has been doing a session searching for three different things, maybe a touristy user, right? And the next query is Eugene district, right? Here are the top candidates that were generated thanks to this personalization, RNN-based hierarchical personalization system, and so on. So you see there are several examples where the sessions are of different sizes, and what you see is the queries that have been recommended by or generated, by this RNN system all seem to be pretty reasonable compared to the ground truth query. Overall, the model has three different LSTM layers. One which sort of encodes each query into a vector, right? The other, which sort of computes a soft attention, and the third, which is basically the decoder. So the three LSTM layers are like two encoder layers and one decoder layer. The encoder layer sort of encodes the queries and then the entire session as well. And then the decoder layer essentially tries to generate the next query. It predicts the map queries according to the fed encoding vectors from the encoder side. Right? So that is how this hierarchical contextual attention-based RNN encoder and the decoder work together so as to come up with interesting suggestions. Um, Another popular method now, so far what we have seen is people trying to incorporate personalization using traditional machine learning methods. You've seen how people have tried to incorporate personalization using RNN encoder-decoder based method, specifically a hierarchical one. Further, people tried to extend this kind of method using attend copy generate mechanism. This is the same as the popular copy generator mechanism for natural language generation models in NLP, right? So uh, pointer generator or this copy generator mechanism became very popular in this time period and started getting used across several subfields in natural language generation, right? And people also started using it for natural language generation in QAC. And that is why we discussed this one in detail. So the concurrence-based models, session concurrence-based models, or even trie-based models sort of suffer from data sparsity and lack of coverage for rare or unseen queries. If you have not seen this particular prefix ever in your query log, there is no way that you can pump suggestions for this prefix using a trie-based solution, right? A trie-based most popular completion solution. And therefore, what you need is to look at other mechanisms, the generative mechanisms to come up with suggestions in such cases. ACG is attend copy generate method, which has query aware attention mechanism to capture the structure of session context, as we will see in the architecture on the next slide. And the other interesting part is that it automatically detects session boundaries. So you don't need to feed in what is the session boundary. Typically, in the search world, a session is considered as a contiguous sequence of queries such that the maximum gap between any two queries is less than 30 minutes. Like 30 minutes is a heuristic thing, and people just use it for the sake of it, right? So as is anyway, session boundaries are not very clear. This model nicely also captures this aspect. The model is based on this broad intuition. The intuition is that within a single session, a large portion of the query terms is retained from the previously submitted queries. And, so people tend to repeat words in queries in their session. And the other important part is people tend to repeat infrequent words, infrequent or unseen words. Okay. So in fact, this is backed by statistics that these authors derived from query log, AOL query log. So around 62% of the terms in a query are retained from their preceding queries. So people tend to sort of 2/3 of the words that they use are just repeats of the previous words. Greater than 39% of the users repeat at least one term from their previous query. So lots of users do this, right? Lots of users of copy terms from their own previous queries. And then greater than 67% of the retained terms, more than 2/3 of the retained terms in the sessions are from the bottom 10% of the terms ordered by their frequency. So people tend to repeat words which are not so frequent, okay, and specific to them, personalized to them. Okay. So let's look at an example about how the ACG model works. So let's say we have a user who has typed 3 queries so far, right? So in this user session consists of 3 queries: Bob Dylan, Forever Young Dylan, and Dylan photo, right? The user is trying to type in the next query, and your goal is to, of course, predict the next query, right? So the copy generator mechanism at any point can either copy a word from the past or generate a new word, right? So at every time point, the model automatically predicts by itself what should be the copy probability versus the generate probability. And what you see here is the output from the model at 3 timestamps. So at 3 timestamps, it sort of generates the next query to be predicted, which consists of 3 words, to be suggested, which consists of 3 words, right? In the first timestamp, it decides to copy, right? In the second timestamp, again, it decides to copy. In the third timestamp, it decides to generate. But if it has to copy, what should it copy? So therefore, it must have some sort of a hierarchical attention on the existing queries. So therefore, it has a contextual hierarchical encoder, which essentially gives an attention at the query level and also has an attention at the word level. So as you see, at the first time point, it says that, hey, copy something from Q1 and well, copy Bob with a very high probability. In second timestamp, it says that, hey, copy. So therefore, it's basically at the first timestamp copied Bob, right? Second timestamp, it said that, hey, copy something from Q1 or Q3, and then copy Dylan with a very high probability, and therefore it ends up copying Dylan here. And the third timestamp, it basically says, no, no, don't copy, well, generate something new. And then it sort of decides to generate the word bio. Overall, leading to a new query, Bob Dylan bio, right? Which is basically the query that the user actually put up in this particular session after, as the fourth query. Okay? So this example was supported by the architecture as shown on this slide. Um, it's an RNN encoder-decoder architecture. It has an encoder part, it has a decoder part. It has 2 levels of attention. And even before that, it has all these words getting embedded by the embedding layer. And then it has an RNN, which basically works at a word level attention and a query level attention. So as you see, there are 2 RNNs, one which is basically processing things word by word. Queries are separated by a special token. And then there is a second blue RNN which processes things query by query, right? And therefore also comes up with query level attention. On the decoder side, it's a copy generator kind of a decoder, which first uses a switch gate to decide whether it should be copying things or generating things. And when it wants to copy, it makes use of this query level attention and the word level attention totally overall to come up with an overall attention, and then decides which one to copy. Even when it is generating, it basically uses this overall attention to decide what to generate. Okay? So the switch gate is essentially learned based on the hidden state on the decoder side, whether it should copy or it should generate. Right. So this copy generator mechanism overall leads to a very effective generative model. In fact, the evaluation was done in two parts, two kinds of metrics, one based on discrimination. So basically just trying to figure out if the candidate query is going to be ranked high up by this copy generator model. So the generative probability is used as a feature, right? And the metric used to evaluate this discriminative power is MRR. The other way of using this model is as a discriminative model, which is basically where you try and come up with various words, and then the evaluation is based on word overlap with the actual ground truth query, embedding based similarity with the actual ground truth query, or retrieval based similarity with the actual ground truth query. In fact, there are three metrics which are used to compute retrieval based similarity with the ground truth query. The first one is pretty simple. It's called retrieves similar search results. It's also called sometimes as SERP sim. So the idea is that you have a ground truth query, you get the top 10 results. You have a generated query by the model, you get the top 10 results, top 10 search engine results. If the results match a lot, for example, their titles and snippets, if you take the back of words, they match a lot, then basically the similarity as per the search engine result page, SERP sim, is very high, right? And that's what is captured in this metric. The second metric is a pseudo relevance feedback based metric. So the idea is that not just you get top 10 results, but then based on them, you expand the original ground truth query or the generated query and get more results. You do two or three iterations of pseudo relevance feedback and then check if the top 10 results match a lot. Okay. So that's the second metric. And the third metric is interesting. So it takes all sessions with a length greater than 2. For example, consider a session with length 4, right? Now you would use the first two queries as input and try to guess the third query. Now, when you have the third query, you basically get the search engine results for the third query. For the generated query. You also get the search engine results for the third and the fourth actual queries, ground truth queries, and then you compare these results, right? So the merged list from the ground truth side is compared with the list of results that you get for the generated query. And if there's a good match, then you basically will have a high SIMRED plus score. Okay. So on all of these metrics, people compared this ACG method with several previous methods. So there is this most popular completion or most popular suggestion based baseline, right? There is yet another baseline with 17 different features, pairwise features, contextual features, and suggestion-based features that we talked about in one of the previous videos. People also compared with the standard sequence-to-sequence learning method with the hierarchical recurrent encoder-decoder method with the current method, which uses query-aware attention only, or which uses the CM part, the copy mechanism only, right? And then they observed that their method, which basically uses the 17 baseline ranker features plus the attend copy generator method, meaning sequence learning, attention, query level attention, and also the copy mechanism, right? That one gives them the best results, gives the best MRR. So not just gives the best discriminative results, but also it leads to the best generative results. Um, when you compare across different methods, overlap-based method, embedding-based method, or even retrieval-based method. So what you observe is that, yes, the ACG essentially already gives you very good results, if you combine it with baseline the baseline 17 features, you get even better results. You get even better interesting results. So that was the hierarchical RNN encoder-decoder framework. Next, I'm going to talk about GRUs with user and time representations. So far, we have talked about personalization from a perspective of using the previous queries or the previous words in the session queries, right? Uh, However, you could also you could also come up with a user embedding and use it as part of these generative models. You could also combine the time information. So although several people have used the session information, they do not care about the time gap between those queries in the previous queries in the session. Yeah. So in this particular paper, the authors have proposed a character labeled two-layer GRU. So here is a two-layer GRU, and it's sort of coming up with character by character predictions for the next character prediction in some ways, right? Uh, the input actually consists of the user embedding part, which is super important, right? Which is different from the previous works, right? Also a character embedding part and the word embedding part. It takes a one hot encoding of the character. It also takes embedding for the word of which the character is a part of, right? And lastly, it takes time embedding also. So time embedding and user embedding are things that no previous work had considered, and this particular work takes it into account. So all of these together go in as inputs, character by character inputs, and then you try to predict the next character and maximizing the autoregressive loss. So basically maximizing the probability of seeing the next actual character given all the previous characters. So the user representation is essentially obtained using the paragraph to vec debo method. So it's a popular method of trying to sort of come up with a user representation. The idea is that you take the previous queries that the user had put up, you take all the words in those previous queries, and that sort of represents the user in some ways. So the paragraph to vec debo method essentially is a shallow neural network with just one hidden layer, which takes a random word from this set of previous words fired by the user as queries. It takes a random word from this set as input, and then tries to essentially, it is trained to maximize the probability of predicting the user u given that particular word. Okay, so it tries to come up with a user embedding in that sense. Okay? That is how these user embeddings are learned, and then you would use those user embeddings by feeding them as input for every character that is passed as input to the GRU encoder. Okay. Time representation, well, so the time is represented as hours, minutes, seconds, and also weekdays. Just like the transform models popularly used the sine and cos based embeddings for positions, these folks basically use the sine and cos functions so as to encode time and pass it also as input for the character based RNN model. Lastly, yet another thing that has been popularly studied for such models is diverse beam search. So when you're generating suggestions, you want to generate suggestions um, that are good in the sense that maximize the probability of seeing the actual ground truth in in the generated output. But at the same time, you also want to have diverse suggestions coming out from the beam. Typically, now there are several ways of coming up with diverse beam search. So people have just leveraged those ways for natural language generation in QAC systems. In such cases, the beam search becomes doubly greedy, right? I mean, in some ways, it is greedy because it tries to maximize the probability and gets the top case suggestions, which have maximum generation probability from a language modeling perspective. But then on the other hand, it also becomes greedy from a perspective of generating diversity with respect to groups of suggestions that are getting generated, right? So therefore, the diverse beam search is in some ways optimizing a doubly greedy objective. Okay, so now overall, these folks sort of compared their system with several other with two other baselines and ablations of their systems. So as you see here, the two baselines are the most popular completion baseline, which is so common, and they also compared it with the NQLN system, which we talked about earlier, the neural query language model with LSTM. So uh, along with word embeddings, character embeddings, one-hot character embeddings, and otherwise the learned character embeddings, and the MPC along with the Lambda Mart learning to rank ranker, right? So their system and where various ablations are shown here. So where there are two suffixes that you see, subscripts that you see. U sort of stands for language model enriched with user vectors. T stands for time vectors, right? So time features. So using, of course, both time and user features basically leads to good results across two different data sets, as you see there, right? Both for seen and unseen prefixes. As you see, unseen prefixes get no results from the try-based most popular completion baseline. Uh, on the other hand, what you see is that if you add diverse beam search and also add most popular completion as a nice feature, and then combine it all with the lambda rank ranker, you get really good results, specifically for unseen prefixes here, for without using lambda mart, just combining these two features for unseen prefixes in the in the biomedical data set. Okay. So typically for seen prefixes, typically you would observe that the MPC-based baseline does well, especially if your data is large enough. But then for unseen cases, as you can see, the try-based baseline, MPC baseline is just not going to work. And which is where you see that this particular method, which was based on user and time embeddings, gave very good results. Okay, so that's about GRU-based method for user and time representations. Next, let's talk about transformer-based hierarchical encoder model. Recently, since 2018, transformer models have become very popular for natural language generation across many tasks, including question answering, summarization, question generation, machine translation, and so on. In QAC, for query auto completion, especially personalized query auto completion, people have also started leveraging transformer models to generate effective and very awesome completions. So what you see here is a network which is a transformer encoder-decoder based network. So you see there is this encoder part, and you also see that there's a decoder part, right? So there are two encoders actually. In fact, one encoder which basically is encoding the user history or the behavior, as you can see here, and the other encoder which is encoding the current user prefix. So both of them basically use transformer encoder layers so as to encode things. Finally, the prefix and the previous behavior encoding is combined so as to generate the queries, generate the next query, right? Or generate the completions for the current query. Um, there is also yet another task which is being done in combination with this query generation task. That is basically the CTR prediction task. So while you're generating the query, you may also want to predict whether this query is going to be clicked or not. Now, based on previous label data, of course, you have information of whether the query was clicked or not, and therefore that label can be actually used to compute the CTR prediction loss at training time. So the encoding of the prefix is pretty simple. You basically use a transformer encoder to encode that. On the other side, the user behavior can be encoded using multiple encoders depending on different kinds of behaviors that might be measured for this user. For example, there are two particular behaviors that these folks have encoded. One of them is the previous queries in the session history, and second is the browsing history of the user. Thus, the overall input to the model is a query prefix, which you see here, and two behavior sequences, one which encodes the search query history and the other which encodes the browsed item title history, right? So you take both of those and you train different transformer encoders, which essentially take tokens from these behaviors and thereby come up with a user sequential behavior representation as a final pooled output. You combine the representations across the two behaviors along with the representation for this prefix, and then try to have a multitask decoder where there are two tasks being done, query generation and CTR prediction. So that's their overall multi-view, multitask, attentive framework. There is also attention that you provide to different representations that you have, the browsing-based representation or the searching-based representation, and thereby come up with a good prediction, CTI prediction, and a good query generation. So here is an example of how their system behaves. This is for Chinese, but there are also English translations. The prefix is sports. Uh, the query context is as follows. The user has searched for such things in the past, in the current session. The browsing context is as follows. The user has browsed these items, these pages with these titles. Right? And what you observe is that this is the golden query. So after this, the user actually completed the query as sports pants for girls. And if you look at the most popular completions, well, these are the most popular completions. If you look at just the transformer-based generator, um, which does not care about the browsing context and so on, you get these completions. But then if you look at their method, which is a multi-view and a multitask method, that gives you completions which are really, really nice, and which of course also contain the query right at the top. The same thing is quantitatively shown across both seen and unseen prefixes. What you observe is that, and these are very different ablations of their model. Do you use the search query history or not? Do you use the browsing history or not? Do you basically use the CTR prediction task or not? And do you use the query generation task or not? And what you observe is that, yes, especially for unseen cases, which is where these generative models are most useful, you observe that the combination of all the four things, the multi-view thing and the multitask thing, multi-view and the multitask thing, both lead to the best results. Right? So they have reported results using various metrics. Blue and MRR are pretty popular. They also came up with this new metric called as unbiased MRR. They said that, hey, different rankings have basically position bias. So users are more likely to actually see suggestions at the top and less likely to see suggestions at the bottom. Can we incorporate this bias into the metric as well? And that is why they came up with this metric called unbiased MRR, where it's basically more or less MRR, but more like weighted MRR. These weights were basically learned based on their query log. So they use the static set of weights, and that is how they've defined this unbiased MRR metric. Okay. Okay, so in this video, I talked about personalization models for autocomplete systems, for natural language generation in query autocomplete systems. Specifically, we talked about these four different things: traditional machine learning based methods, hierarchical RNN encoder-decoder method, GRUs with user and time representations, and also transformer based hierarchical multi-view, multitask kind of method. Okay. Thanks for watching. Hope you liked the video. Uh, Feel free to connect with me on LinkedIn or know more about my research on my home.